Good morning, guys. I'm a bit late. Running around here.
Good morning.
I guess I'm not late. I'm just not as early as I normally am. Yeah. Hey Scott, this is the first time you've been on this particular call, the main call, right?
Second, I was on last week. I'm just sitting in for Howard because he's running the
Yeah.
Boston Marathon.
You were on last week, but that was the interconnect call. So this is the first time you've been on the group call. So
Okay.
yeah, you're not in my. I've got just a track attendees, so I just
Yeah. Howard's running the Boston Marathon today.
Oh, nice. Okay. Morning, everyone. Good morning, all. Sorry, I'm just playing a little bit of catch up here. Morning, Matt. Morning, Bijan. And Michael.
Good morning.
Good morning, Alan. Hi, everybody.
Hey, Bijan, is there any get together of the OCP thing in Portugal next week?
There's a social event if that's what you're asking about. I don't know
Not
the
one
details.
of the project leads like you did the global one.
No. Because of the travel situation, not everyone could come, so we decided not to do that.
All right, that makes sense. Yeah, I actually arrive about 5 p.m., so I might grab a late beer if you're
All
around.
right. I'll be around.
All right, sounds good then. We'll make it a two person and see if we can recruit anyone else.
Open invitation for everyone.
There you go. Let's spread the word. Good morning, Anna. Can you hear me?
Good morning.
Is this your first time on our call?
I think I was on some previous calls with OCP.
Yeah, but this particular high performance compute one?
Not your one.
Okay, great. Well, welcome aboard. That's perfect. When we get going, we do introductions. So it's you and Scott will do a very brief introduction. And so I guess Sardina is the name of your company. Is that right, Anna?
Yes, Sardina Systems. We are software. We deploy a cloud infrastructure.
Okay.
Also for research companies. So in our internal mailings,
Yeah.
that it can be useful to join to listen.
Okay. Yeah, no, great. That so I'll give you a chance once we get everyone on the call and we formally get going. I'll give you a chance to give a brief introduction so that everybody can hear it. All right. So welcome to the group anyway.
Thank you. Nice to meet you.
Okay. Good morning, Jeff. He's still connected. Morning, Jeff.
Hey, morning, Alan. How you doing?
Good, thanks. Okay, we're 8:05. Let me just capture the attendees here. Morning, Munir. Okay. All right, let me share my screen here a moment. Okay, can everybody see the minutes?
Yeah.
Okay, great. Let's make it a bit bigger for people. Okay, great. Welcome aboard, everybody. This is the OCP High Performance Compute sub-project, our main meeting. And today, I just had really two topics. The first one, I was chatting with Jeff Mersham, who's on the call, and he was highlighting a number of other potential avenues that might align with our efforts. So the effort we're putting behind the New Frontiers proposal might be, because we're putting that effort behind it, whether that comes off hold or when that comes off hold, that's one opportunity. But if we've got the meat in a proposal, then we could potentially apply for different avenues of funding, was what Jeff was making the point on. So basically, I'd like to hand the floor over to Jeff on that particular point and let him just talk about these other funding avenues. And then I submitted my final presentation for the regional summit, and I wouldn't mind doing a quick rehearsal with you guys. It's a little, if you heard the other one, it's a little bit more information. I've got some the reason for me presenting, or I'm diving into details, it's giving me a bit more data to put into the proposal as well. So on the back of this presentation, the extra work I've put into this, I'll also help to outline some of these subsections of the proposal. So I would like to go for that with you, get your critical feedback. Feel free to give me a hard time.
Alan, can you add my name, please?
Yes, I have got it. I just haven't put you on the filter yet, so I'll update it.
Okay, no problem.
Yeah, I've got you on my main spreadsheet. It's just I have to manually bring it across. It doesn't automatically update anymore for some stupid reason.
No problem.
Okay, so without further ado, let's get into the introductions. So I believe we have two new people on today. Scott Shuey, would you like to start?
Yeah, I'm Scott Shuey, technical manager. I cover a lot of different standards for LOTS. Right now I'm sitting in for Howard Andrews, who is running the Boston Marathon today.
And LOTS are?
We do connectors, cables.
Okay, great. All right, thank you, Scott. Welcome to aboard. And Anna, would you like to give an introduction? You're on mute if you're talking, Anna. Can you hear me, Anna? Is Anna still on? Oh, it looks like Anna's dropped. I guess she decided the meeting wasn't for her.
Mm-hmm.
Okay, and it looks like we've got another new person. Would you like to? Sorry. Have you been to this call before?
No, actually, it's the first time on my.
Okay. So first of all, would you mind? What's your affiliation and yeah, what's your affiliation, Wee? Who are you with, and can you give a brief introduction to yourself?
Yeah, actually, I'm working on a small edge AI company from China.
Okay.
Yeah. And I'm responsible for product marketing. So that's and the ecosystem.
Okay. And your and the name of your company is?
Cellphone.ai.
Cell phone, as in CELL?
SOPHON.
SO. Say that again, sorry. I missed it. You're on mute, Wee. Wee, is it SOPHEM?
Thought he said PH.
SOPHON.ai.
That SOPHON.ai? Sophon?
Yeah.
Okay, great. Thank you, Wee. Welcome.
I get the reference.
Sorry.
Oh, I was just saying, I get the reference. That's from the three body problem.
Oh, is it? Nice. Morning, Nat. I just seen that Nat Nugent just joined.
Hey, good morning, Alan.
In the PQR. Make sure I capture everybody. All right.
Hi,
Okay,
Aaron. This is Jason. Yeah.
Oh, and Jason. Hi, Jason. Welcome. You
yeah.
just got me as well. I'll make sure I capture you as well. So we got a lot of. Thank you all for joining. All right. So just capturing everybody. So so Scott's introduced herself. Anna's decided to leave the meeting, and Wee Wee's introduced herself. I think that's everybody. All right. So on to the next topic, which is other potential funding avenues. Hey, Jeff, I haven't really done much since our long conversation in the week. Would you mind just taking the lead on this in terms of the ideas that you were, in the different NSF things that we talked about?
Sure. So yeah, what we were
If you want to take control of the screen, I can really, because I guess you were showing some web pages of potential funding avenues. So if you want to share your screen, then you've got that option.
Sure. Yeah, let me grab share screen option. So what we were discussing was more around the idea of the New Frontiers project seems to be put on hold, but will be coming out. And as such, there's other opportunities that can be used to help improve that submission by submitting to other, forms of government funding options that are out there. And so one of them was out there was around this NSF, right? National Science Foundation. And so they do a lot of what's called SBIR awards SBIR is a Small Business Innovation Research Award. And they do these awards for, new types of, innovations in different areas. And you can see some of the areas here: biological science, computer information science, engineering, geoscience, etc. But, and then there's this technology innovation partnership thing. So if you click on the computer science one, you can kind of go down and you see a list of just different funding opportunities that are available, and what they have going on. And this is kind of like listing all of them in here that are in the different directorates. So there's like, 5 different directorates that are involved in the computer science one. As you can, limit it here as to what you want to search. But it kind of goes by due date of when the next required, things available. So there's a whole lot of different projects that are in here that can be funded. And so these funding can, the smaller ones are the ones that, and they still have like phase 1, phase 2 submissions, etc. So you can continue to win a phase 1 SBIR and then apply for a phase 2 that's of a larger dollar value, that will enable more of the development of the technologies. And so these ones here are really meant for standalone businesses, that can go in here and do these. And then you can see the due date for the proposal that they have here. So May 2nd is pretty close. But there's the other one here that's called this funding search by the TIP. So this is for this is the one that comes down to this one here, the Technology Innovation Partnership one. Takes you here. So this is the TIP one. And so the TIP one is basically a pull together of multiple companies. So it's not a single company submission for a grant or an award. It's a multi-company submission one. And so it usually has somebody who's the CEO or the program manager for that submission, right? Which is a great role that Alan leads here as well. But it allows other companies to get involved in the submission for larger dollar value projects. So it's more like, instead of making an award for a single company, they're awarding for a much larger project, right? A much larger initiative with multiple companies involved that are doing it. And everything would be ran by whoever's the program manager on the thing, pulling all the people together, pulling the submission in, and you do have to make a proposal, right, that goes in. And you can see the different types of ideas and proposal type things that they have in here. But again, these are larger dollar value ones, or larger bets that the government's making on a much bigger size project. And so they believe that having an award that goes out with multiple different companies is going to lessen the risk of, that company going under or whatever, which is always the case, because these are only for small businesses, of a individual award. So you can see here in all of these ones, there's letters for details. So some of these are like continuing open submission type things. Some of them do have proposal deadlines for more specific type things, but typically you can find things in here that will kind of feed into what the team is doing here. And it'll be a way that we can all work together to basically take the same proposal that's being developed right now for the New Frontiers project, continue to build upon that, use that as a submission into one of these NSF, projects, and then turn around and NFS is really good at giving you feedback on your proposal. So if you didn't win something, they'll say why. You can have a meeting with them to say why you didn't win it, right? What you need to do for next time. And then you can make quick turnarounds of that, you know, fix things and resubmit it again. But it's a way that we can continue to build out the capability and the submission going into the other project by using one of these. Now, these aren't the only SIBRs that are available out there. There's also ones that you can see. Hate this top-down thing that I can't get rid of. Am I still here?
Yep, yep, we got you.
Okay. I clicked the button. I wasn't exactly sure what all it was. There's another one for DSIP. I'm loading a page here. So these ones are DoD related ones. NSF is NSF. The DOE actually also has, you know, Department of Energy also has ones that are available too. This one's the for the items for the DoD. And typically they have a lot of very unique ones, but at some points they also have ones that are more open to ideas. Like submit an open one. We don't have a particular topic of this one, do it. A lot of the DoD ones in here can be pretty specific into exactly what they're looking for. And you can see whether these ones are, you know, these ones are Army ones that are in here. Some of these are like more competition style ones, tech scale AI, tech scalable AI 2, you know, as a follow on for it. You can see when the thing's open, when it closes for submit. The close here on this column is all for the submit date of the solicitations. And then you can click the link to find out more about the solicitations. If there's any Q&A on it, you can find out here as well. But you can do like a quick read of these ones to find out a little bit more about what they are, what they entail, whether it's a, you know, kind of a fit here for the group. But these ones are specific items that are to, you know, specifically for DoD. There was another there's another list of different ones here that are STTRs. So an STTR is typically involving some organization, research institution, which I think, and I'm not sure, Alan, but I think, you know, maybe, you know, typically it's more like a university type thing, an organization, nonprofit. But I think maybe OCP might be able to fit into this, into a STTR. Now an STTR typically has a lot less amount of submissions go in. So typically it's a higher acceptance rate for STTRs because they typically involve more than one company. And a lot of companies aren't willing to give up the funding for, you know, for an organization. But in this case, they do that. And you can see these ones are here by DARPA as well. So these include everything in the DoD, which is also this research institution here. These ones don't have anyone that are particularly tied to it. But like I said, there's other funding opportunities that are available out there that can be done. And you know, you kind of just go off and find them. I think the NSF ones are a little bit more flexible in how they work versus the DoD ones. They're a little bit more open to, hey, you create the proposal as long as it kind of fits within some of these higher level buckets, right? Especially the tip ones, because they're multiple company initiatives. But again, it's just an area that the team here can continue to build upon the technology, build upon the, you know, the proposals, and go off and win some awards that, you know, can be used to go actually build this next gen, you know, HPC system.
Okay, thanks, Jeff. Just another one that popped in my mind that I think I have mentioned before is the National Renewable Energy Lab. That's another possibility because we're on the energy centric computing side, sustainability, and the energy recovery in particular, I saw the presentations at supercomputing from NREL and the European one on reusing the energy. And I spoke to the presenter there, and he did say they have proposals can be submitted. So that might be another one as well, just to add to the list. So,
yeah, I highlighted one that I thought could be kind of one of interest for the team to go after.
Okay, nice. Yeah, also deadline on that, June 20th. So that's a half decent deadline that we could.
Yeah, you do have to submit what they call a preliminary proposal. So it's typically like just a 1-2 page type thing, highlighting what you're doing. And
okay, and that's the June deadline for the preliminary. All right, okay.
Yeah, that's the preliminary one. And then when you submit, you can submit it earlier, and they can say, yeah, we accept your idea. Why don't we want you to submit a full proposal?
Okay.
And so you can send in a preliminary one just to see if there's a fit with what they're looking for within this. But it's a really small thing, and Alan, you could probably do that all by yourself with the information that's already in the other one.
Yeah, but I guess in general, what I found encouraging from the conversation with Jeff was really that, hey, we've got a number of opportunities. So we're all trying to rally around getting a proposal for the new frontiers whenever it gets whenever it comes off hold. But this, I guess, the message here from my perspective is the effort we put into that proposal is not wasted effort if we don't get the new frontiers. I think we have a number of opportunities here. So, and we might have to just tweak it for each of the different applications, but the meat of it that people contribute to this document hopefully can substantially stay the same. And again, what I'm doing is I'm going to put more framework in there after the OCP regional summit from the little bit of extra work I've been doing with the subgroups, specifically the thermal one and the universal interconnector are a couple of key features, which unless we've got anything else, Jeff, I can switch over to doing.
No, you take on.
Okay, all right.
I'll put this one in the chat here, so it's a quick link to it.
Okay, great. Well, thank you for that, Jeff. Much appreciated. All right, so if I can take over the sharing of the screen again. I'll switch over to. Okay, I'm going to try and do this as a as a formal presentation, if you don't mind. So it'll again, I know that some of you have seen this, but I'm trying to get my timing right, etc. So it should be about maybe about 12 or 13 minutes is a sort of target we've got. So that's what I'm shooting for here, and we've got the time. And so if you let me present this, if we can avoid questions, just so I can go through the full rehearsal, and then we can dive into questions and recommendations and comments on how well I did. All right, thanks. Right. Okay, good morning, everybody. My name is Alan Cantle, and I'm the OCP High Performance Compute Sub-Project Technical Lead. And today I'd like to present on progress toward an open and sustainable energy-centric computing architecture for today's AI and high-performance computing applications. Give you a quick overview first. I'm going to be talking about the high-performance compute module we've been conceptualizing, which can be potentially used from HPC and data centers all the way to edge computing. I'm not going to have time to give you the detail, but I did give a more developed overview at the OCP Global Summit in 23. If you enjoy what you see here, I would thoroughly recommend that you go and watch that video to get a little bit more detail into the module itself. But today I'm going to focus on efficient power delivery, how we're doing that thermal management concept, including energy reuse, and a new universal topology interconnect idea. And I'll give you a summary and a call to action. So first of all, I wanted to just touch on the NVIDIA Blackwell system, which was announced a few weeks ago, and really show how this highlights the power, thermal, and interconnect challenge of today's AI racks. So we have the racks laid out here, but if we look on the left, we've got a complex hybrid liquid and air cooling. It's a blind mate, this rack, into the chassis, but it also has air cooling. You can see those bank of fans at the front. So you can see that we're now introducing this liquid cooling or hybrid approach. And then from a power perspective, we've got a whopping 120 kilowatts in the rack. And in terms of power delivery, we have facility power to 48 volts at the top and bottom of the rack, feeding a bus bar, similar to OCP rack 3, and then going up and down the bus bar, and then long cables in the chassis going to a power distribution unit, and then back to the point of load of the devices that are being powered. So we have actually around 2.5 meters, up to 2.5 meters of copper to get that 48 volts in, and then down to the point of load voltages to the devices. So quite a long distance there. And finally, we're noticing that we are moving away from PCB traces towards cables. You'll notice there's no motherboards in any of these boxes. They're all just rather large modules, some of them, with a Grace and 2 Blackwells, or just smaller ones with just NVLink switches. And you can see in the one on the left, you can see the cabling to the NIC, the InfiniBand cards at the front. And on the right, you can see the actual NVLink switches with connectors right next to the chips themselves, doing cables to the backplane that goes up and down the rack. So hopefully you can all see that the concepts that we've been thinking about for 3 years inside OCP HPC and saying we need to radically redesign, this is proof that we are now hitting the challenges we've seen for over 3 years. So what we're looking at is we've looked at a composable high-performance compute solution, and we call it our OCP wall of compute. If we take a look at the supercomputer Frontier, it's actually made up of about 50,000 CPUs, GPUs, and switches. And our implementation, we can make our implementation with 50,000 high-performance compute modules. And that's the module on the right. Another little point to bear in mind is AI has insatiable need for memory bandwidth and capacity at low latency. And we're seeing in our typical high-performance compute, we have our storage, or we're now calling storage even memory. We need fast access to those. Is separate in traditional HPC, and that's 50 picojoules per bit or more to move that data between the two. And we want ever-increasing bandwidth, so that's a problem. Whereas the architecture of the HPCM has the media of all sorts coupled tightly to the big processor, and we're in the 1 to 2 picojoule rate. So this is one of the first energy-centric focuses of our architecture. Taking a closer look at the module, effectively, it's roughly the size of an EU brick. So all in all, we're just another brick in the wall. It's basically a composable domain-specific architecture building block. And it's inspired by the OAM, the OCP accelerator module. It can support any processor accelerator or switch in the region of up to 1 kilowatt of power. And it has 16 E3.S modules for the media. We have direct water cooling with energy reuse, and there's H universal topology interconnect. So we can potentially have 8 terabytes per second of co-packaged optics bandwidth connecting between the modules that are populated on the wall. And it's scalable from the HPC to the edge. Here's a nice little diagram from ChatGPT of a Lisbon street with a telecom box on the side of the road. And we've got a 6x6 edge compute, high-performance compute telecom cabinet here. And we can populate that with the HPCM modules. The power will come from underneath the street, and the water can feed into the city heat network, like there is a city heat network in my hometown in Bristol, UK, for example. Or we could take a smaller 4 modules and actually get it designed into a house system as like another type of utility feature, where the modules can either heat the hot water and or contribute to the heating of the HVAC system by being plumbed in natively. And then you can buy your gaming PC modules and plug them in like so. So instead, I have friends with teenage boys. They have 800-watt PCs and their bedrooms are getting really hot. It's a nightmare for them to manage. So this would be a good way to go for our industry. So we've got one module for all types of compute, from HPC to cloud and edge. Taking a look at efficient power delivery, just referring back to that copper loss through the distance on the NVIDIA Blackwell setup, you can see that our module, the lower picture, we are really close. So facility power goes through an in-wall 48-volt power supply, and then a very short connector to the module and to the point of load feeding the high power chips. So we've got a tremendous opportunity for much lower cost because there's much less copper going around on feeding this power, or stroke and less loss because we have higher efficiency in terms of the losses, in the copper losses. Moving on to our thermal management concept, this is quite a radical concept, and I want to make sure you understand this is completely unproven. It's hypothetical. We've been discussing it in our work groups, and it's quite interesting to me. So firstly, I want you to emphasize, take a look at the middle piece. This is the module itself, the HPCM module. And so the water flows through the veins of the manifold where the pluggable modules are, so we can conductively cool the pluggable modules in active cables. And then it rises into a little tiny immersion chamber to actually cool the big kilowatt processor. We want the power out to be ejected at 65 degrees C. So we have a local control loop on the module, restricting the flow to ensure the water always ejects at 65 C. And we step and repeat that 8 times for a column of 8 of these modules in the wall. At the top of the column, we have a heat exchanger with the facility inlet. And again, we have the similar control loop for maintaining reusable energy out of that control loop. And finally, we have this liquid ring vacuum pump to pull a 0.2 bar pressure vacuum. And at 0.2 bar, water sort of boils around the 65 degrees C mark. And I'm reliably informed by our contributors in our work group that that's about 11 times more efficient versus single phase water. Also, the immersion cooling unit is potentially going to use a conformally coated copper high performance compute module, and University of Illinois has stated that they think that's 7 times more power per unit volume of copper efficient. Finally, if we can use water, we're up to 4 to 9 times better thermal conductivity than PAO or Florinut. And if all things being equal, if we put that together, we would be greater than 300 times improvement over conventional liquid cooling techniques, which is astounding in terms of the potential of this. But I want to emphasize again, this is completely unproven. We need your expertise to actually make this work. It's a complex, free-nested control loops going on here, so we need that. Just looking at water, there are water use concerns. It's electrically conductive, but the conformal coating should isolate that. We've got bacterial growth, so we need to somehow design and eliminate stagnant water areas. But our water temperature may help because it's a lot hotter, but there are different types of bacteria that can grow in hotter temperatures. Corrosion, material mix issues we need to be careful of. And water treatment, we could still do water treatment, but that reduces thermal conductivity, and it gives us additional sustainability concerns. So we'd like to just stick with pure water. Looking at the universal topology interconnect, a diagram on the right here, you can see there's 8 topology interconnectors. So we can connect hypercubes, meshes, etc. between these modules with cables. And we're trying to standardize on the standard PCI SIG MCIO connector is our current plan of record. The protocol is agnostic. Anything PCIe, Ethernet, NVLink, HDMI, InfiniBand, whatever protocol we want to support over these universal cables. We're standardizing on 8 lanes from 32 gig all the way up to 224 gigs, so we can support the fastest speeds. We're trying to get a little bit more intelligent on sidebands instead of using 70s technology. So we're using the OCP LTPI tunneling protocol, separate clocks. and we just have one static pin for the cable present. And then from an active cable option, so we can support retimers and near packaged optics cables. You can see on this paddle card, there's an active PCIe retimer on this. And so that can fit in the paddle card in an active cable. And on the right, you can see that on the cable itself, we have a little thermal pad, and we have a mating mechanism where we can mate to the water manifold. So we get a good conductive path for cooling that 10 watts of power, and we don't need huge OSFP cages, etc. Here is an optical example using the Avicenna light bundle IC on the right. And you can see there's a hole in the paddle card on the left. We populate that, we flip the optical module over. If we flip the board around, we can see the optics coming through with a little alignment ferrule. We then plug in the passive optical fiber cable, and that makes our active optical assembly. And again, that chip on the other side has a little copper mount to firmly conduct to the manifold. If we zoom into the actual module itself, here I'm showing 4 of the Avicenna light bundles with populated above one connector. So it's on the same side as the big processor, and you could have chiplet interfaces as well if we made the module an entire chiplet substrate. And if we flip on the other side of that and zoom in, you can see the 4 light bundles popping out there. Each one of the transmit and receive are each a terabit per second each. So that's 8 terabits per second, giving us a terabyte per second per connector, and 8 terabytes per second for the 8 connectors. So we're at HBM bandwidths going module to module, which is pretty damned impressive. So that gives, oh, and there's the optical ferrules that you'd make to get couple into the fiber. And the key thing here is this allows us to do any topology interconnect, between modules at this interconnect. The other thing about using the fiber is it's far less dense in the cable bundle diameter, so it would be more sympathetic to the routing options between modules. So in summary, we've got bold ambitions to bring our open compute architectures into the 21st century. We're very focused on a sustainable, energy-centric computing first mindset, and it's really core to our vision. This requires innovations through collaboration across all our industry silos. And believe me, that's the biggest problem and the biggest challenge we have. That's why, that's what we're doing. Thermal management is a major challenge, and we have some crazy ideas. And AI and HPC require system I/O bandwidths to skyrocket, and we need to plan for this in some more elegant fashion from the top down. Revolutionary changes require open collaboration, and I'd really like to thank OCP for giving us the ability to do this in the OCP HPC sub-project. So we still have got a long way to go. We're filling concepts. We need help to bring the HPCM vision to a reality across all the broad industry disciplines as they're labeled there. So if you're in any of these, come and help us. Help us convert our naive thermal management concept into a reality. Help us to realize the universal interconnect that supports an evolving I/O landscape. And there's all the details of how you can come and join us. Thank you very much. Okay. Oh, was it 14 minutes and 38 there? Let me just... I presume everybody heard that, did it?
Let's go.
That was great.
Yeah, okay.
Yeah, that was very nice.
Thank you. Any points of did it? I guess we all know it, right? So it makes sense to us. I'm a little bit concerned that people are. Oh, thank you, Bijan. Damn, I had to file the final presentation yesterday, so it'll.
I'm sorry I didn't review it beforehand.
No, that's right. I posted it last night at 7 p.m. There's no chance.
Hey, Alan.
Yes.
If there is one suggestion, I would say you are too humble. I would not call your idea naive. Because if you say your idea is naive, then people may not take it seriously. Just say, I would choose another word. Don't say naive.
Yeah, that's a good one. And that I think there's a British personality of me coming out there. I think I'm guilty of that. Whenever I introduce people to, like companies to come and join us, I am a little bit too honest with my, hey, look, you know, we're trying to get funding. There's no guarantee. We got none of the big guys are interested in what we're doing. You know, so I'm not good at encouraging people to. I don't like bullshitting. I guess so I do. I mean, I'm a good systems engineer, but I think my in terms of pulling these things together, you lot have helped us to make over 3 years. It's a slow, steady slog, but contributions from all of you have made this better and better over the years. And like that thermal one in particular, it's a complex control loop. And I think that the beauty of that idea is this is something that I don't think the thermal experts, the people in the thermal industry really have too much of an understanding of control theory. It's certainly in complex, a free level complex control loop. And there are loads of issues with it, like the valves will fail, therefore the reliability, it'll be a nightmare maintenance wise. So there's lots of reasons. I find when you got brand new ideas, there's always lots of reasons for somebody to say why it won't work. And they've got very good reasons. And so I don't like to sound too confident, because in reality, I'm not that confident. I need the experts to iron out the problems, and we need to do this in an open community. So anyway, but your point's well made in that. I do know that I suffer that trait, and maybe I'll change that word.
Okay.
But thank you. That's good feedback.
Yeah, Alan, I think overall, I mean, I think I've told you this before, I like everything. You know, I was thinking though, maybe it would be important to either mention or show like the problem that or at least restated the problem that you're solving for. Because, you know, if you look at kind of other approaches, like the existing approaches, I guess you'd say, all of that just depends on scale. Like, you know, they're just going to scale up, right?
Yes.
And I think if you considered all the dimensions of this as like in a polar type of chart, then I think this approach actually would look a little different, you know, from a polar chart than say, you know, a National Labs approach or IBM approach or whatever, you know.
Yeah.
And so that might be worth mentioning. Like, you know, like for example, you know, it optimizes for heat reuse, or it optimizes for the reduction of copper, or whatever it is.
Well, I guess that's what we're trying to cover. It does optimize across all of them. It's like in any one particular person's discipline, it does optimize. But when a person from that discipline sees the optimization, they look at it, they say, oh, well, you know, I get it, but it's marginal. It's only really slaps you across the face when you see them adding up across all of the different disciplines, you know. And that was why I showed the Blackwell. I think the biggest one, though, there's two. So let me just share my screen again. The two big ones, I think, that I need to emphasize, to your point, Bijan, is firstly, this one here is, and Blackwell suffers this. If you look at Blackwell, apart from HBM, this is nothing but a processing machine. It's a CPU-centric first architecture with fast memory bolted on. And AI needs far more capacities, as we've seen, right? And so then they put it to Grace, and Grace is giving you LPDDR memory to get you an extra terabyte of memory. But that's nowhere near enough for the trend in AI. You need gargantuan amounts of memory at massive bandwidths to make that happen. So what the key thing difference from Blackwell to us is we said we need the processing in switches and everything to be tightly coupled where necessary to the media, and lots of it. And so this 1 to 2 picojoule per bit interface versus a traditional HPC having a separate thing with a very thin pipe, you know, this 50 picojoules per bit isn't a problem normally, because you're only going a couple of terabits per second or terabytes per second. But when you want to do, terabits per second. But when you want to do many terabytes per second to this storage, this becomes a huge power number when you multiply it by the bandwidth. So we need more of this. And so this is this is a main feature, I think, of our architecture.
So would you be able to call this approach compute and memory? Or
yes, it's memory centric. In fact, if we go back to my OCP Global Summit presentation, I actually present the architectural argument of a data centric approach and why we're going this way.
Well, so what my point is though is that you and someone else said it, like you're understating it, you know. So if you look at the optimization of this system, compute and memory approach versus a traditional approach, it's massive. If you look at the scaling, right?
Yes.
So here you have mentioned one thing. You've mentioned a 2 picojoule per bit power impact, energy impact versus 50, which is, you know, like 20 times less or whatever. But you know, also there's a latency value.
No, absolutely, and that's the thing. When you think energy centric, you sort of get latency for free because data movement is the biggest energy consumer. So the way to reduce energy consumption is to make things closer together, and you tend to win latency wise. The other point, by the way, just to the 2 big points that I think make our architecture so significant is the composability of the domain specific, you know, Hennessy and Patterson domain specific architecture composability is we can compose any configuration. We can make a Grace hopper. We could remove these modules and put 7 PCI links between 2 modules, and we make a Grace hopper configuration. Or we can wire a frontier node configuration, 4 GPUs per CPU, or a Summit, 3 GPUs per CPU. Or we can do whatever. We can mix and match. And us is somebody wanted to make a one-off machine that maybe wants one FPGA with 1 GPU, with 1 AI chip, with 1 CPU, with 1 whatever, right? We can wire those exactly as our application needs. So we get rid of unnecessary switches, etc., which means we get rid of unnecessary power burning. For a general purpose machine, we can make a very specific machine just to be great at our application.
So I don't think I've asked you this question, but can you do true heterogeneous computing? Like,
yes, that's the whole idea. That's the whole point, is each one of these modules can be any processor you want it to be.
That's massive. Alan, you need to tell the story at the end.
Watch my global one. It's in there. let me bring it up, because
I don't think the point is coming across in this slide.
No, tell me about it. I've been doing this for 3 years. I know it's not. Let me HPC the next generation. Here it is. This is a presentation I gave last October. So the slide here. So first of all, I start with this and I say, look, everything's going crazily changing. That's my example there. Here's where I talk about data centric, right? So the data plane continuum. I talk about tiered memory, and I talk about the coupling of memory tightly to the processor. And I say, then it's a simple Lego block step and repeat on our cloud and edge. Then I have the little video animation of the module itself. And then this is the one we're talking about. So let me just play this slide. So I say we've got the wall of compute. We've got 1 module, and we've got a wall, 8 modules tall and however many long. So I said we just populate that into our wall, right? And then I say, if you wanted a dual frontier node, you know, this is a box. This is a 1U box in frontier. You want 4 GPUs per CPU. So we've got this layout. and you so we can make Frontier, and then you cable the topology to be exactly the same as Frontier, and this HPCM will run Frontier software stack. So we can replicate Frontier easily with this. Now, there are some technicalities we'd have to discuss. If we wanted to tightly couple a CPU with a GPU, let's just say Grace in Hopper. Grace Hopper has 7 times the PCI bandwidth, and it's only 1.3 picojoules per bit compared to 7 picojoules per bit for PCI. They say so this for the same energy they can do a terabyte per second. Well, we can just connect 2 of our modules together. Instead of media, we can just connect the PCI buses together, CXL, and we've got a Grace Hopper configuration. We can match Grace Hopper. Or if we go back to the IBM and NVIDIA Summit nodes machine, that was a 3-to-1 GPU with Power 9 CPU. So we can make that. That's a different topology to the Frontier. We can wire that up, and we can make a Summit machine with a Summit software stack. And by the way, IBM pulled out of the high-performance compute industry after Summit. Oak Ridge loved the Summit node. They loved the Summit machine. But they pulled out because no one wanted a configuration of 3 or even 2 GPUs to CPU. And so they couldn't sell it to anyone else. And it was a loss maker for them. So they just said, we're fed up with this because government high-performance compute is a very specific computer that you can sell to nobody else anymore with this heterogeneous computing. If you want a GPT-3 optimized AI cluster, you have to make an AI one, and you just step and repeat them and connect them all together, like Grok are talking about. If you want an FPGA pool, you can have just FPGAs, like CXL likes this pooling idea. You could have optical switches, so we can actually put an optical switch into our module as well, and we actually make it like that.
Okay, but what?
And finally, Burger King, compose it your way. Any mix of all of these, you have a Burger King heterogeneous computer. There you go. That was happening.
Yeah, no, that's exactly what I'm talking about. Also, maybe my ignorance, I'm sorry, but aren't there 16 slots on each one of those blocks?
Yes. Yes, 16 here, yes. And so yes, correct. Let me if I just play. So this is a module. These are the 16 E3S modules being ejected. And so they have media in, but they could also have mini accelerators in them. The main way to think about the difference between the module, this module itself is a kilowatt module, right? And the media you should look at as a low power, like a media and a low power accelerator. So we're sub 100 watts for the E3.S, and we're in the region of up 200 watts to a kilowatt on this module here, is the idea. Oh, hang on a minute. Why did that not? Anyway, so yeah, and then it puts it back together. So these are the only 2 building blocks we need in the entire industry. So, dare I say it, the box builders, the industry would change to an infrastructure industry where you build a data center with the walls of compute, the empty walls for the sockets for plugging these modules in. And then a vendor of an accelerator would build an HPCM module with their kilowatt accelerator or switch or whatever. And then vendors of media would build their media devices, like Samsung with their CXL.mem, etc. And maybe even some smaller accelerators where you don't need a kilowatt, but maybe 40 watts is fine. You could plug in heterogeneous accelerators in the E3S modules, but they're the only 2 building blocks of our entire industry. And so you don't need a Supermicro or a Dell or anything. You just buy these modules from your industry and you plug them into your rack. It's a bit like the old world of analog computing. Remember all the cables on analog computers? You wire it together to your need. And then this one here is, I'm trying to tell the CXL, so this is why I'm at the composable memory systems innovation, is I'm trying to say, hey, we can do a little benchtop 4 modules, and we can wire an AMD MI300 with an Intel Agilex FPGA with an Infabrica switch and a bunch of media, Samsung and Micron media modules. And so in a lab environment, in a university, you can build any heterogeneous computer you want. And then on the chiplet enablement, I'm talking to John Schaff and the gang today, because they're now beginning to think about system management. You know, these chips are getting so big with the chiplets. Why don't we make the HPCM or the OAM module the substrate, which then plays to the optical thing that I just showed with Avicenna? Suddenly this could be 25 millimeters here. So we can have like a half a picojoule per bit interface go into the Avicenna from a processing chip. And then we have optics coming out in a nice thin optics cable. And so it's all this is a mechanical and an electrical infrastructure. It's so simple what we're doing, but we're trying to think about, and anybody can make any machine they ever want out of 2 module formats. That's the message. So yes, I gave that presentation that you're talking about in the last in the OCP Global Summit. Does that make sense, Bijan?
Yeah, no, it makes sense to me.
All right, so but that's the thing. It's a complex message, and I think it gets lost because it is a systems approach, and everyone you typically speak to typically have expertise in one of the disciplines, like they're a thermal specialist, or they're a software specialist, or they're a whatever specialist, and they don't really get the magnitude of everybody cooperating together. And when we architected this, it's like the big challenge of compute today, as we can see in the Blackwell platform, is thermal power delivery, thermal management are the 2 big ones. And we've put that as center stage, and energy reuse for sustainability. So that's why we said we need to do a Elon Musk first principles approach to this. And then I can build any computer I want. And by the way, people like me, little one-man bands, can suddenly say, I've got a good idea for a computer where I want a bit of FPGA, a bit of GPU, and a bit of CPU, and I want them wired like this. I can buy the modules and wire them. I can't do that with an NVIDIA DGX. I got to buy everything NVIDIA. I can't do that with anyone else. And if I'm a startup, like one I'm working for, Next Silicon, I want to be able to just build a module and be part of a whole ecosystem. But if you look at the disaster of the startup industry, Samba Nova and GraphCore had to raise $1 billion of venture capital money because they couldn't just make the silicon and a module or a PCI card. They had to build a chassis. They had to build their own rack. They had to build their own data center. They had to build their own software stack. They had to build their own management stack. And then they could begin to compete after spending $1 billion of VC money. Meanwhile, NVIDIA's moved on because it took them 5 years, and now they're going bust. And so it's not sustainable. So it's anti-competitive the way the industry is right now. I want to bring all these silicon startups. I'd rather they take a few $100 million and they have a chance to compete in this new heterogeneous world. That's what I'm trying to do.
Raspberry Pi meets HPC.
You got it. Exactly. We've had that conversation before. On the button, Bijan. That's it. It's the Raspberry Pi ecosystem. The embedded ecosystem, the IoT ecosystem is flourishing because of Raspberry Pi. You build your entire machine with Raspberry Pi and attachments, and then you can shrink it down to a widget if you want to when you get a volume application. With this, we don't ever hit the volumes of IoT, so we're trying to make a system where it could actually be deployable as a one-off machine just for CFD, or a one-off machine just for movie rendering, Darwish. So that's what we're trying. That's what I'm trying to do. Trying to wrestle this out of the incumbents, and that's why the incumbents aren't interested in joining this group. They've got their incumbent business. If this works, suddenly we've democratized the whole industry. But I can't get the government to understand it. I can't get anyone to understand this. Anyway, sorry for the passion speech.
Yeah, no, I don't mean to.
No, that's fine. No, that's good. No, thank you, Bijan. The fact that I'm loving this conversation because it's, even in our own work group, it's coming to fruition that people that, I don't know how well the pennies dropped with the various people that attend, but there's been lots of regular attendees that do sort of, I think, get the general bigger picture. And
so our next step is we need to build some.
Exactly, and that's what I'm trying to do. If we could get the New Frontiers money or some money, and somehow, how do we funnel? The problem is, Bijan, is the government knows how to contract in a round robin with having one throat to choke, like IBM or HP or whatever, right? And they really want to give this to a whole group of like 100 startups or 100 smaller companies and have an open solution. But they have no idea how to manage that. And to be honest, it's like herding cats, right? I mean, when you've got small companies, it's like herding cats. So we need a system integrator that has intelligence. So Paul Hartke from Xilinx kept nagging me to become a DARPA program manager. He said, you should run this under as a DARPA program managed project. You're the program manager, but this isn't DARPA hard. I think cross-silo collaboration is DARPA hard, personally. And but DARPA doesn't see that. You're not making new science.
But I think in a, maybe in a kind of crawl, walk, run mode, like there are definitely some, RISC-V startups that we could certainly work with that would be interesting,
but
and certainly be interesting.
well, by the way, actually, just on this, there is a convergence going on. I know we're over, guys. But this is a good conversation. There is a convergence that Bijan, you and I both know about, right? We've got OAM v3 we're talking about now because we're going, oh my God, look what NVIDIA have done with Blackwell. How are we going to compete with OAM? What's v3 going to look like? Well, v3 could look like HPCM, as you and I have discussed. Secondly, we've got ODSA changing to the open chiplet economy, saying we need a system level platform. So when we do our little chiplet modules and we connect them all together, how can we plug that into an existing platform of computing pieces, other heterogeneous pieces, and we can get our little chiplet collaboration running? We could do that. HPCM could be the chiplet enablement platform. So we cover OAM v3, the chiplet enablement platform. And then we've got the CXL, Composable Memory Systems work group, trying to build composable memory systems. And that's why I'm on that innovation move at the regional summit. I can solve the CMS with HPCM. So from an OCP perspective, HPCM covers the 3 big serious bases. If only we could get, now the trouble is the big boys with the money, the Intels, the AMDs, the Googles, or well, certainly Intel and AMD, it's all about what does Facebook want to buy? What does Meta want to buy? And if there's a commercial opportunity and Meta says you've got to have in an OAM format, then the Intel will throw 100 engineers at, make the module in OAM format, pay the ODMs to partake in OCP, and get it as an open mechanism. So, but it's still a commercial deal. But the beauty of ODSA that BAPI did and what we're doing is I have no commercial. This is just a passion project for me. I want to do for my industry to re-enable the ability for small companies to become part of this ecosystem instead of it being owned entirely by the big guys. Anyway, there you go.
I have to drop for another meeting. I appreciate you taking time to answer my questions. I'm really excited. I want to push this forward. So let me know what I can do to help.
Let's have a chat over a beer. Let's do that beer on when we arrive on Tuesday then next week, because I'd love to. But thank you for the questions. They're perfect. I mean, it makes me happy that the points that are becoming, everyone's beginning to get it in a lot more detail now. So that's great. That's very nice to hear.
Thanks for your hard work. I gotta run, but we'll talk later.
Yeah. All right, guys. Thank you all.
Bye.
See you later. Bye.
Have a good one, Alan.